Hello, in this lesson, we are going to talk about how to solve simple exponential and logarithm equations. Okay, this is in your homework number 7, right? So let's look at some examples. The first example, I take the first question from your homework, which is 3 to the power of x is equals to 9. Okay, to solve this equation, we actually have multiple methods to solve it. Okay, so I'm going to address them one by one. The first method I like to talk about is the function method. Function method. Okay, what does this mean? Right? What is the meaning of this equation? Right? We're solving for x. Solving for x. What does it mean? Well, it actually means, right? We don't know the input. And the input is applied a rule. And this rule, of course, the input is going to be powering, it's going to power 3. Right? So the rule of the function is 3 to the power x. And the output is 9. That's what it means. So this is actually an if statement. This is actually an if statement. As we understood, right? We mentioned these earlier in other lessons that it's just an if statement. If the output is 9 for this function, right? And with unknown input, we don't know the input, and we're looking for what input will make the output to be 9. So that's the sense of this question. Okay, that's the sense of this question. So the first method, right, graphically, is that you look at 3x, right? You graph it. We have graphed this function before, right? So let me make some adjustment to graph this function properly. And we have, I'm going to make some adjustment for the graph, right? And we know the domain and range for this function. And right there. Okay. And let's just make it scoot over a little bit and make some adjustments. So that's 3 to the power of x. 3 to the power of x. So we know the output. We know the output. The output is 9, right? The output is 9. What does that mean? Well, horizontal cut, right? Horizontal cut. So we draw a horizontal line, right? The horizontal line crosses the curve at a point. Okay, and the point of at the point of intersection with the curve, right? And that point has an input and output. Has an input and output. And that input, of course, is x. And the output is 9. So what input will cause the output to be 9? That's the nature of the question. That's the nature of the question. And the x, right? X is horizontal as input, right? X is horizontal, right? Which is right here. This is x. And the y is vertical, whatever color, right? Y is vertical. Okay, so this is 9. Right? This is 9. And this is x. And x is what we are looking for. X is what we're looking for. So this is the context of this question in the function perspective. So you can see this is very similar to what we did with the equations we've done before, right? The trig equations and so on and so forth. Now, the question is, what is the answer? Well, the answer is what is the horizontal, right? X is sorry, this one I want to be color the same, right? X is horizontal. So when X is equals to 2, Y equals to 9. Therefore, the answer to the equation is found. Okay, so X is equals to 2. So that's the answer. Okay, so this is the context. This is the context in the function's perspective, in the function perspective. So here I'm going to just draw the graph and put the point, right? So it doesn't move around, right? So this dot, X is 2, Y is 9. So let's make it a red dot. And that's the solution. And this point, we can mark it. Okay, let's mark it. 2, 9. Do we have other inputs, right? Look it up. Do we have other inputs? Right? Do we have other inputs? And there. So 2, 9. Okay, so let me scoot it over a little bit. Let me just make it scoot over a little bit. 2, 9. Okay, so the nature of this question, right? The way we solve, we see it from the function's perspective because we know the output, so we draw a horizontal line. Okay, so this is the first method. This is the first method. Second method is more algebraic. Second method is more algebraic, right? Since we know that 2 to the power of x is equals to 9, and 9 is 3 squared, right? And this function is 1-to-1, okay? Therefore, x is going to be equals to 2. And this reason I like to mention, because 3 to the power of x is 1-to-1. Why this reason so important? 1-to-1 function says the different input produces different output. In other words, if we have different output, then we have different input. And in the other words, it's saying if the inputs are the same, the output is the same. In other words, right? So all these are different ways of saying it. So 1-to-1 function means the following. As a 1-to-1 function, so let me put it as a note, okay? As a 1-to-1 function, if a function is 1-to-1, right? So we know the definition, which is f of x1 is not equals to f of x2, right? That means the output are not the same whenever the input is not the same. Okay? And from this description, right? So whenever the inputs are different, then the output are different, right? In other words, or we can say, i.e., right? If the outputs are the same, then the input must be the same, right? Because it's 1-to-1, must be the same. Okay, so these are the outputs. Output is the same, therefore the inputs are the same. Now, so this is note number 1. Okay, number two, if the function is not 1-to-1, then we cannot do that. If the function is not a 1-to-1, we cannot do the following. What is that following? Right? So that is if f of x1, then x1 is going to be equals to x2. So this statement will be wrong if it is not 1-to-1, okay? The key word is not 1-to-1. So this statement will be false, okay? So here I have an example for you, okay? Examples. It's very important to understand these examples. The first one, right? A simple example. F of x, suppose f of x is equals to x squared. Right? Can you, well, negative 2 squared, well, negative 2 squared is equals to 2 squared, right? Can you say negative 2 is equals to 2? Obviously not, right? So, but negative 2 is not the same as positive 2. That's example number 1. The next example, right? Example number 2, we know that x squared is not a 1-to-1 function, right? Example number 2, let's use our trig function to explain this, right? If sine, can you say that if sine 0 is equal to sine pi, which is true, can you say 0 is equals to pi? Of course not, right? So, but 0 is not equals to pi. So this is why that when we go from this step to the next step, you have to guarantee the function is 1-to-1. Okay, very, very important to understand this concept. And we will be using this in the future for other situations. Method 3. Method 3. Okay. Method 3 is using definition of logarithm and exponential. What is the definition of logarithm and exponential, right? We use a definition of logarithm. Logarithm, right? Logarithm. What is definition of logarithm, right? Log base b of omega is equals to triangle if and only if, of course, provided the base is larger than 0, not equals to 1. So b to the power of triangle is equals to omega. And of course, we always have that in our mind that b is larger than 0 and not equals to 1. Okay. In this case, in our situation, the base obviously is 3, right? So what we have here in comparison with the definition, right? So let's do a matching, right? So this is 3. Right? This is a 3. Base is 3. So base is 3. Omega is 9, right? And triangle is what we're looking for. So this is a 9. And this is x, right? Because 3 to the power of x, and this is x. You see, if we use definition, right? Then our next step would just be what? X equals to log base 3 of 9. Log base 3 of 9, we know that's equals to 2. So this is using definition. This is using definition. Are there other methods? Are there other methods? Okay. The other method actually is also there. Method 4. This method is taking logarithm on both sides of the equation. Okay. The narrative is that if, right, we know that the solving equation is if, right? It basically said if 3 to the power x is 9, right? So in this case, we're going to take a logarithm on both sides. Logarithm on both sides. But when we are doing this, there's a certain assumption. Okay, what do you think is that assumption? When we take logarithm of any base, we need to remember logarithm's domain is a positive number, right? Is 3x positive? Yes, 3x is always positive, right? That's the range of the function 3 to the power x. 9 is positive. So when we take a logarithm on both sides, you can actually take a logarithm of any base. Okay, so I'm going to take a logarithm. I can take a logarithm base 3. Okay. And I take logarithm on base 3 on both sides. We can take this, right? When we're taking this, we must understand that this function, log base 3 of whatever, right? This omega must be positive because this is related to the domain of a logarithm function. And we studied the domain of logarithm function, didn't we? And 3 to the power x is always positive. We know that 3 to the power x is positive. And that's about the range of 3 to the power x. And 9 is positive, needless to say. Only under these circumstances, you can take a logarithm on both sides, okay? But taking a logarithm with any base, okay? I want to mention this because you can take logarithm base 3, no problem. You can also take logarithm with base 10, base e. Okay, so I'm going to show you how to do that. If I take base 3, right, and the next step, right, that's going to be we can apply the property of a power property, right? So x will bring down the power, which is put in front, and log base 3 of 3, that's equals to 1. So this is multiplied by 1. And x times 1, of course, is 1. Log base 3 of 9, that's equals to 2. So that's how we get it. We got the answer. But I just mentioned it can be any base. It can be any base. Yes, I mean any base. Okay. I can also take the logarithm of a base common log. Okay. I can take a common log on both sides. Of course, I need to use the same base. If I do this, what will happen? Right? I can still bring the x down using the power rule. I have a common log 3. On the other side, I will have log 9. Log 9 is equals to log 3 squared. Right? If I use the power rule, that's equals to 2 times log 3. Okay, let me remind you of the power rule. The power rule basically says, okay, log of any base, right? And you have an omega and raised to the power of heart, for example, okay? Anything. And that power can be brought to the front. And you still have your log base b on omega. So that's the power rule. And in our case, of course, R is a common log. It's a common log. Okay, so as a result, now we got to this point, right? We got that. And then we're going to divide both sides by log 3. Remember, log 3, these must be together. So the next step, I'm going to divide both sides by log 3. Log 3 together is a single number. It's a single number. As a consequence, and you guys need to practice this, okay? Make sure you practice this, okay? So base, if I use a base 10, right? Base 10. If I use base 10, could I use base E? Yes, we can use base E. Okay, if I use base E, what does that mean? I'm taking, so from 3 to the power x equals to 9. Okay, I'm going to take a natural logarithm on both sides. Well, they're both positive, right? So I can, right? So the domain requirement must be satisfied. Any logarithm, right? Log 10 have the same domain, right? We talked about them before, right? So common log, right? And right, for common log, the omega must be positive too. And for natural log, right? For natural log, ln must be, oops, never mind. I need to do this over, okay? So for E, I'm taking ln, right, natural log 3 to the power x equals to natural log 9. And that reason I like to mention, right, is natural logarithm, right? Ln of omega, this omega must be positive too, right? So we satisfy all the domain requirements, then we take a logarithm, yes? And this time we use a power rule again, right? We use a power rule again. And what do we get? We will get x times ln 3. On the other side, we get ln of 3 squared. Oh, 3 squared, sorry. And then that equals to 2 times ln 3. And now we're going to take these and divide both sides by ln 3. Okay, we're going to divide both sides by ln 3. ln 3. Right, so once again, treating ln 3 together, this is a single number. This is a single number. So as a result, okay, x equals to 2 again. So these are the 4 basic methods. And of course, for solving this particular question, you will choose the simplest possible, isn't it? Right? You can choose the first one. And most likely, I imagine most of you probably would choose the second method. It's so straightforward, right? It's so straightforward. However, each one of the methods we talk about here, they all have their applications in other situations, right? So we just take this opportunity to address these 4 methods, So right away, right? So in this question, you probably just solve it with method 3 or method 2. Method 2 is most straightforward, right? It's just so straightforward. But you must understand you can only do this if you can do this only if the function is 1-to-1, and 3 to the power x happens to be a 1-to-1 function. All right, so without further ado, so let's look at the next question. Okay, example number 2, right? Example number 2. Example number 2, we have 3 to the power of x equals to 5. Okay, we're gonna look at the 4 methods right here. We're gonna look at the 4 methods here. The 4 method, of course, the first method would be, first method is what? The first method is a function, right? The first method is function. So we're gonna bring the function method, right? Method 1. We have the graph of 3 to the power x. We understand the context, but this time is not, the horizontal line is not of y equals to 9. The horizontal line this time is y equals to 5. There. So the crossing is no longer the point that we had before, right? It's not the same point, okay? And the 2, 9 is no longer relevant. It's going to be a different point. It's going to be a different point there. So what is this point? Right? The meanings to stay the same. The meanings stay the same. So what do we mean by the meaning, right? The height, well, the horizontal measurement, which is what we are looking for, right? That's what we're looking for. It's not going to be precisely 2 because this time the output is 5. And the vertical is 5. The vertical is 5, right? 5. And this piece or this piece, that's x. We don't know. So how do we find it? How do we find it? Right? So which method will work? Which method? Well, every method will work. Okay. It's just how you do it. It's just how you do it. Okay. You can use definition, right? We certainly can use definition here. We certainly can use definition here, but you can see the meaning of these input output. It's the only thing changes the numbers and the meaning doesn't change. And we're looking for input such that, right? So we're looking for inputs, and after the function 3 to the power x, right? The function, which is 3 to the power x, and the output is 5. It's an if statement. It's an if statement, right? And 5 is not easily represented. Well, here I do have some ways to show you, right? How about we try definition, which is the second method, right? Isn't it second method? Actually, it's not second method. It's not second method. We could use second method. Okay, we could use second method. Okay, in the second method, basically we use is a one-to-one function. So I still put a method. You can see method 1 is difficult to identify x from the picture. Since we have a 5, it's a little difficult to represent it. But don't forget, we have an interesting property that we have learned before. Okay, what is that property? Remember, we actually talk about it, right? The property we talk about is that any base to the power of log base b omega is going to equals to omega. Do you remember that? We actually talk about this. We talk about that since omega is any positive number, right? Because omega has to be in the domain of logarithm, log base b, so omega must be positive. But this also tells us that any positive number can be represented this way. Okay, so 5 is no exception. So for 5, how do we express it? 5, how do we express it? If omega is 5, then this is a 5, right? And base, what base would you like to choose? Well, I like to choose base 3. So this is 3 and base 3. You see that? So 5 can be represented using this expression. It just happened in the last question, right? In the last question, the number in the place of 5 is 9. 9 is 3 squared, right? 9 can be represented as 3 squared, but here 5 is represented as this form. Okay? Well, because 3 to the power x is a one-to-one function, therefore what? Trust me, most people don't use this method though, okay? But I just want to bring this up to show you there are more than one way to do things. Okay, so x is equal to log base 3 of 5. Okay, so in this case, of course, it's difficult to identify because this number is not going to be as neat as 2. But this number does exist. You actually have a numerical value, but we prefer this form. We prefer this form. You can do change of base if you want. You can do change of base if you want. Okay, you can do change of base if you wish, right? So method 1, you can see is difficult in this case, right? To identify that point. But because we have this number, so we can still use the algebraic way. We can use the algebraic way to identify the point. So in these cases, the algebraic method becomes more important, So that's the x, right? X comma y, y is 5, right? Y is 5. So, so let me mark it for you here. So this point, right? The x is log base 3, 5. The output is 5 at that point. Okay, so make sure you take a note on that because we're going to have to erase it because these two software don't talk to each other. Okay, method 1, method 2. As you can see, if we simply use a graph, sometimes it's difficult to identify the precise value. That's why we need to have algebraic method. Okay, so without further ado, so we did method 1 and method 2, right? Method 2, and we still use this one-to-one function, right? So all of these. Method 3, we use definition. Right? So let's look at method 3. How did we use definition? Definition. How do we use definition to solve this equation, to identify the input such that the output is the given? Well, we use a definition, right? So what is the definition? Use definition. Right? The definition says logarithm, okay? It doesn't matter which side you do it. A log base b of omega is equals to triangle, right? These are all just symbolic placeholders. And if that will be b raised to the power of a triangle, and then that equals to omega. And base, of course, is greater than 0, not equals to 1. So in our case, right, in our case, we've done similar things before, right? So base is 3, right? Base is 3. So I'm going to bring this, just bring this under, okay? For our comparison, it just make it easier. 3 is the base, so b is 3, and so b is 3, right? Omega is 5, so this is 5, and here's 5. And triangle is x, right? Triangle is x, and there you go, x is found, right? So using definition, how much step you need to write? You don't need to show these. You just, the next step is you just tell the reader the definition, from definition, x equals to log base 3 of 5. So all the work you have to show is this much. And you're going to be getting better. You're going to be getting better. Okay, so this is the third method. This is the third method. Okay, the third method. How much work you need to show? Just 2 lines. Just 2 lines. Okay, all of these is just my analysis, is just to demonstrate to you. Just demonstrate to you. Okay, so to show work, you really just need to show this much. Method 4, taking logarithm on both sides. This method is not uncommon because in many cases we get to use it. We get to use it. Okay, so taking logarithm of any base on both sides. On both sides. And oftentimes when you do this, you have your favorite logarithm to use. You know, I encourage you guys to use natural log. But before you take a logarithm, you have to make sure both sides are positive because of domain requirement. Okay. Note. Okay, when you do this method, you need to be aware log base of anything. You can choose any base, right? Omega. This omega, the domain is that it has to be positive. So this must be observed. Okay, you will see that if this is not observed, sometime you might be in trouble. You might be in trouble. Okay, we're going to have examples coming up. We're going to have examples coming up. So we're taking logarithm on both sides. This time I'm going to just use natural log. Okay, I'm going to just use natural log. So I'm going to take ln on both sides. I can because both sides are positive. And then what? Power rule. So I get x equals to, x times ln 3 equals to ln 5. And then I'm going to divide both sides by ln 3. Remember, ln 3 and ln 5, they each are single numbers. Single numbers. Okay, so ln 3 is divided on both sides. So ln 3 and ln 3 are reduced because this is a single number, inseparable, and therefore x is equals to ln 5 divided by ln 3. And then you may say, wait a minute, didn't we have a different number before? Didn't we have a different form? Yes, we have a different form. Are they the same? Are they the same? The answer is yes. If we use change of base formula, okay? Change of base formula. What is change of base formula? Log base of the old base, right, on omega is equals to log base of a new base on omega divided by log base new on the old base. Okay, change your base formula. I just make it larger for you. So using this base, change your base formula, if I choose base E as our new base, right? So I will have ln 5 divided by ln 3. So they are actually the same answer, Okay, so this is for number 2. Okay, I'm going to save number 3, number 4 for you. And let's look at a little bit more complicated questions. Let's look at number 5 and 6. Okay, let's look at number 5 and 6. So this is going to be our example number 3. Example number 3. On example number 3, we have 2 raised to the power of 3x minus 5 equals to 4. Equals to 4. Okay, can we use function method? Of course, you can use function method. What is the rule of the function? What is the rule of function? Well, this function is curved at your fingertips. So function method is still there, okay? Especially in these days and time. Graphing, to see a function, to visualize the answer, is not that difficult. But the question is, from the graph, sometimes it's difficult to identify numbers or inputs precisely. That is the issue. That is the issue. So that let me still talk about the functions perspective, right? So you have x, right? And this input is going to be, we're going to do 3x minus 5. And this produces output, and that output is going to be given to the exponential function, 2 to the power of, whatever the input, right? So I'm going to put a symbolic, expression there, make it, I'll just make it spade, how about that, right? And it produces output. So the output is 4. The output is 4. So you would look at these 2 functions, and in particular, you can just graph this function yourself. Okay. If you have an electronic device, if you don't have an electronic device, you have to know how to move around, and that may not be really worth your while. I don't see most of you will do that. But if the graph is at your fingertips, right? So just for the idea, for the sense, just making sense for us, right? So let me just give you the graph, and I certainly just graph it, graph it by whatever I can do at my fingertips, right? So there you go. So I get the graph. I can make some adjustment, right? I can make some adjustment over here. Let's see how it looks, right? So this graph is going to be very different. It's going to be very different from our other picture, but you will still be doing the horizontal line cut. Okay, so that is the key to this question, to the function perspective, right? Whatever the graph, you're going to do the horizontal cut across the curve here, right? But so our job is to identify how much is this much. Okay, so this is just a little bit. So we just need to identify how much is this much, right? We know the vertical is 4, right? You can see the ideal function, even though we may not use it very often because it's difficult to identify the precise value of the input we're looking for. But it does give us that visual. That visual. So with this understanding, we still have a hard time to identify what x could be, right? It seems that between 2 and 3, and what is exactly? Well, right now, we just want you to understand this visual. I want you to have this visual in your mind, even though we cannot identify it. Make a connection with it. Trust me, it's going to help you in the long run. Okay. So anyway, so we're gonna seek out the algebraic method. Okay, so let's look at the algebraic method. Method 2. Method 2, since I have 2 to the power of, this is the question, right? And 4 is 2 squared. 4 is 2 squared, right? And 2 to the power 3x minus 5 is actually a what? It's actually, you can think of it, right? So when we do method 2, what I would do, let me put a think out aloud here. I put a think out aloud here, okay? I see this equation, okay, this equation, I would treat this piece as a heart. I make it more abstract, right? So this whole piece is one entity. So I know 2 to the power x is 1 to 1. And therefore, my heart, the heart I have is going to be 2, right? And of course, we can replace the heart, but so this is what we envision. Okay, so with that thinking out aloud, let me make the fonts a bit larger so you can see the negative sign. So this is my thinking out aloud, and that's what I saw. So I see this as what? As just one entity. So this is my one entity. But when I show my work, I'll just write 3x minus 5 is equals to 2. Okay, and 3x equals to 7. Right, so become solving a linear equation. So at this point, I got x is equals to 7/3. And we found the solution. You can see 7/3 is going to be extremely difficult to identify here. So now with that answer, we can go back to the picture and mark the points. So the meaning of this graph, the function perspective, is still very important to us. It's very important to us. Okay. And that point, okay, I'm going to mark it. Okay, I'm going to mark that point. The input is 7/3, and the output is 4. Okay, so I'm going to mark it. Right, I'm going to mark it. So we can see, understand the meaning, the horizontal, the vertical, right? After all, you only deal with horizontal and vertical, really. Okay, trust me. That's all we deal with for a very long time. Okay, for a very long time. So hold on, let me just move this over to see if that will make a difference. Okay, well, 7/3, 4. Okay, could I do a little bit better? Let me just indulging myself just to make it a little bit more clear. There we go. Whether it works or not, there we go. It's much better. You can see the meaning, right? We know the output, we draw a horizontal line, but it's hard to identify the input from the picture. That's why algebraic method is more important. Algebraic method is more important. Method 3 is coming. Okay, method 3 is coming. Okay, so before we do that, let me show you how much work you need to show. How much work we need to show. Okay, show work. Right, show work. That's all you need to show. This is how much work you can show. Okay, it could be 3 lines, just 1, 2, 3 lines. Okay, the third method is still I want to be consistent, method 3. Okay, for method 3, I'm going to use definition. Okay, I'm going to use definition. How do we use definition? Right, definition, you will also treat, right? So I'm going to think of this as think out aloud. Right, so in definition, what I'm thinking is I'm thinking 2 of this little piece, right? It's just the heart. So in this sense, I'm using definition, right? So the heart is equals to log base 2 over 4. You see that? Okay. And of course, when I write it down my work, I will write 3x minus 5 equals to log base 204. Log base 204 is really 2, right? That's a familiar number. And then we go about to solve, you know, the rest of the steps, 2 more steps. And we're done. And we're done. Finished. So if you use a third method, right? You can even remove this piece. Okay, that's fine. So you visual, this power part, it's just one entity, just one entity. Okay, that's method 3. Method 4. Okay, taking logarithm on both sides. Okay, take logarithm with any base on both sides. Okay, this method is very, very commonly used. And we're using this method even though it's not always necessary, because in the future, when we get to complicated questions, we will. Okay, so in this case, you can choose a logarithm you want to. You can choose log base 2, you can choose log, natural log. So if I choose log base 2, that seems to be the most natural, right? So if I choose base 2, right? If we choose base 2, no problem, right? So you have both sides are positive. How do I know? Because 2 to the power anything is always positive, right? So I'm going to choose log base 2 and log base 2 on both sides. And what do we get at the end? And then we apply power rule, right? So you get 3x minus 5 equals to 2, and the rest is pretty familiar, right? What if I choose log base e? Okay, what if I choose base e? No problem, base e. If I choose base e, right, to this equation, if this is true, then I'm going to choose ln. Both are positive on both sides, so I can choose positive. I can take a natural logarithm. And now what do we get? Is that we're going to have to bring the power 3x minus 5 to the front, and natural log 2, and that equals to natural log 4. 4 is 2 squared, right? This parentheses is absolutely necessary. Don't miss this parentheses. If you miss this parentheses, you're going to miss points for that step, and it may also affect your later steps. Okay, depends, right? Depends. And ln 2 squared equals to 2 times ln 2. Okay, so in this situation, the next step we get is going to be 2 times ln 2. before we go further, right? Make sure you understand ln2 is one single number. They are inseparable. ln and 2 are inseparable. So treat ln2 as just one single number. So what I would do is that I'm going to divide both sides by ln2. Okay, you don't have to do this. You can distribute, but this will make it easier. Okay, this will make it easier. So ln2 as a single number will divide into ln2 as a single number. So the next step, you get 3x minus 5. And the right-hand side is a 2. Okay. And of course, the rest is straightforward. We already know. The rest is straightforward. All right. Let's see. Okay, some of us may not, from here, they may not divide ln2 at the next step. In case, right? In case someone or somebody, okay, from here, this is somebody did not do dividing ln2 on both sides. So what this person might do is that distribute ln2 to inside the parentheses. If you do that, okay, there's a lot of, I want to talk about this because in the future you may encounter a situation you have to do it. You have to do it, okay? So what you do is you treat ln2 as a single number. So ln2 is going to multiply 3x. Okay, it's going to multiply 3x ln2 minus 5 times ln2 and equals to 2 times ln2. If you choose to distribute, that's okay. That's not a problem. Okay, you just make sure you treat ln2 as one single number. And then after you've done that, you might notice that ln2 and ln2, they are like terms. So you're going to add, okay, you're going to add 5 times ln2 on both sides. As a result, okay, you have 3x ln2 and you have 7 times ln2. Okay, which is 2 times ln2 plus 5 times ln2. You see that? Okay, and that is 3 times x equals to 7 times ln2. And then you divide both sides by what? What do you divide both sides by? Certainly you divide both sides by ln2, right? But you also want to divide both sides by 3 times ln2 because you want to isolate x. You're going to divide both sides by 3 times ln2. You divide 3 times ln2. Okay? Well, you can divide in separate time. You divide ln2 and then you divide by 3. You can do that. But you divide ln2 and ln2 reduced, right? And 3 reduced. So as a result, x is isolated, and which is 7/3. Okay, so this piece may look to be pretty complicated. Okay, but the lesson to be learned here. Number one, that you try to reduce it so you don't have to deal with the complicated situations. But when you have to deal with the complicated situations, you want to make sure you know to handle it, because in some situation, you will have to deal with those complicated situations. One of the lessons we must learn is that ln2, you must treat ln2 as a single number. ln and 2 are inseparable. They are inseparable. This is a single number. So you can see no matter what you do, any method you use, you're gonna get the same answer. You're gonna get the same answer, okay? So that's number 5. I think I will save number 6 for you, number 7, number 8 for you. And let's look at number 9. So this is going to be our example number 4. Okay, so we're solving for x. E to the power x equals to 5. Once again, the first method, I really want you guys to get to the function perspective. It's so helpful, even though sometimes we don't get the answer, we cannot find the answer, but we get to use the perspective, the vertical cut, horizontal cut, and so on and so forth, back and forth, back and forth. In this case, of course, we know the output is going to be a horizontal cut, right? And e to the power x is a function, right? So x and is the input for e to the power x. E to the power x. And we know the output is 5. Right? So naturally, we're going to graph it. Right? We're going to graph it. And here we go. Right? We graph it. Let me just do a little bit organizing so we can see the picture better. Okay. So this may be something like that. Oh, there. My bad, I made a mistake. Okay. And just let the graph scoot over a little bit so we can see it better. And here we go. We got e to the power x. Right? This is e to the power x. We're being very familiar with it. We know the output is 5, horizontal cut. Horizontal cut. Oh, wait. Horizontal cut. There. And what is a crossing? What's a crossing? You can see the meaning the same, right? The meaning the same. And this is the output, right? The height is 5. But what is the input? What is the input? The input is very difficult to identify. It looks like it's more than 1.5. Right, so let me use a different color for input. Okay. You can see we know the value doesn't exist, right? So these pictures tell us oftentimes the answer does exist. It's just we cannot tell what the answer is precisely. So this is our x. Okay, so that visual is very important. That visual is very important. Okay, so then we have to resort to the algebraic method to come back to graph it. Okay, and we'll come back to this. So method 2, right? Method 2, we have e to the power x equals to 5, right? Can 5 be represented in terms of e? Yes, it's actually e to the power of ln 5. Okay, so what property did we use? What property did we use? Okay, we used base raised to the power of log base b of omega, and that equals to omega. Okay, so our omega is 5, and we chose e as our base, right? Omega is 5. Of course, omega need to be positive, right? And 5 is positive. If 5 is positive, we can represent it, right? We can express it. You guys are going to use this form in calculus, guys. Okay, don't ignore it. learn how to use it, okay? In calculus, the one you use most often is the base E. Okay, it's a base E. So it's ln. You have plenty of practice at in your homework, right? So this case is that case. All right. So once we have done that, you can see x is going to be what? ln 5. And we understand we can do this because e to the power x is what? Is a one-to-one function, right? E to the power x is a one-to-one function. Oops, what am I doing? Wait. Is one-to-one. Is one-to-one. Okay. We have talked about the reasons before, right? One-to-one. Method number 3. Okay, let's wait. Let's do it. We need to go back to method 1, right? Because we couldn't identify the value. So now we can. The input is ln 5, the output is 5. So we got that red dot with a horizontal line cut, and that horizontal line is y equals to 5. Y equals to 5. Okay, that horizontal line is y equals to 5, right? Horizontal cut. And now shall we mark the point? Sure, why not? Right, so let's mark the point as ln 5 of 5. And where should it be? It should be, let's put it just 4.5. I'm just estimating which place it should be placed, right? It's trial and error. So it looks like I should move it. I should move just a little bit. Okay, to see if that works. There we go. So input is what we're looking for, right? Input is what we're looking for. All right. Okay. You know what? Actually, maybe we would also mark the horizontal line this time. We didn't mark it before. So this is a y equals to 5. So where should I put it? -1. So maybe 4.5, right? Just to have these essential information on the graph will help us a lot. So we can remove those temporary writing. Okay, so that's the second method. Method 3, definition. Definition. Using definition is probably the most common methods. The most common method. So using definition, you just get x equals to ln 5. Okay. I hope by this time you guys are okay. If you have any questions, please don't hesitate. Method 4. Okay. Taking logarithm on both sides. Taking logarithm on both sides. With any base. Take logarithm with any base on both sides. Even though very often we tend to use natural log, and I encourage you guys to use natural log more. But I still want to mention that you can take any base. You can take any base, okay? So because e to the power x is always a positive, you see this piece of information about e to the power, the range of e to the power x. It's very important, okay? We need to use it. We need to use it because when you take logarithm, you know, ln omega, right? So that omega must be positive. You can see we actually use domain and range quite often. Okay, we use domain range. So making these connections in our thoughts, essential. It's absolutely essential. This is part of the training. Okay, so we can take natural logarithm on both sides. And the left-hand side, right-hand side. And the left-hand side, of course, is x, right? X times ln e. Ln e equals to 1, right? So this equals to 1. And 1 times x is x. Therefore, x equals ln 5. That's it. So the answer is ln 5. Okay. So let's look at some more examples, right? I think we have most type of examples covered. Let's pick up 2 more. Okay, this should be number 5. Example number 5. Example number 5. This one I choose e to the power of x. E to the power x equals to 0. Okay, it's still the same drill, If x is the input, the function, the rule of the function is that we take that input and we power e. And the output is 0. So if the output is 0, give me the input. Function perspective. Method 1. Okay, did we do the graph? Ln e to the power x? Yes, we did it. But that was the output was 5, right? So now everything has to be changed, right? Everything has to be changed, right? And the red dot is gone. The red dot is gone, right? And this time it's going to be 0. Right? The horizontal line is going to be 0. So I'm going to draw a red line here. Okay, I'm going to draw a red line here. Let's see what happens. No touch. No touch. If there's no touch, what does that tell us? No solution. No solution. No touch, no solution. Do we have to use other methods? Really, there's no need to do any other methods. But I do want to mention another method. Okay, I'll call it method 2. Okay, you don't have to use a graph to make such illustration. Okay, what you can say is that your answer can be saying no solution because, okay, e to the power of x is larger than 0 for any real number x. That's it. Okay, that's it. And let's look at that's example number 6. Okay, and this time we have e to the power x equals to -3. So if we draw the same picture, and this time the horizontal line is going to be what? What will be the horizontal line? Right, so let me bring that function perspective, right? That function perspective, now the output is -3. So the horizontal line should be what? The horizontal line should be -3, isn't it? There we go. It doesn't show, right? Well, because I didn't include that part in the graph. No touch, no solution. Okay, so if you use the first method, right? No solution. Again, second method, right? Second method, the same argument. The second method is same argument. exactly the same argument, right? Of course, this equals to -3. So this will never happen. Okay. So these are the examples that we covered about solving exponential equations. If you have any questions, please let me know. And thank you for watching.